When you've completed this lesson, you should be able to multiply and divide numbers that contain units and obtain answers that correctly express those numbers in units. You will be able to express numerical values and units in prefix notation, such as 3.4 millimeters. You'll be given an equation with several terms. You'll be able to check the dimensions for each item and then check the equations as a whole. And you'll be able to convert a physical quantity expressed in one set of units to an equivalent quantity in a different set of units. Photonic technicians are required to work with measurements that come in many different units, sometimes English, sometimes metric. They frequently need to convert between different systems of measurement. For example, the speed of light may be given in 186,000 miles per second, or 3 times 10 to the 8th meters per second. Or you may encounter wavelengths of 0.555 micrometers, or nanometers, or angstroms. Let's look at an example problem such as the heat transfer rate in a laser. Delta Q over delta T equals delta M over delta T times C times delta T, where delta Q over delta T is the heat transfer rate, delta M over delta T is the coolant flow rate, C is the specific heat of coolant, delta T is the temperature change of the coolant. And you measure the temperature change of 17.7 degrees C with a flow rate of 33.3 grams per second. Then the coolant specific heat is 1 calorie per gram degree C. What value of units do you record for the heat transfer rate for this laser? We're going to return to this problem after we develop the skills to handle all of those different units. Measurements that you take should always include a value and a unit of measure. For example, 10 feet should always be recorded with both the 10 and the feet. 20 miles per hour, or 3 cubic centimeters. Never just record the number without the unit of measure. Always record both the value and the unit of measure. When measurements are multiplied or divided, we handle the values and the units separately, but we handle them both. For example, if we multiply 10 feet times 20 feet, we'll multiply the values 10 and 20, and we multiply the feet and the feet to end up with a result of 200 feet squared. If we multiply 20 miles per hour times 10 hours, we multiply the values 20 and 10 and the units, miles per hour times hours. You'll notice that the hours in the denominator and the numerator will cancel, leaving us with just 200 miles. If we divide 5 grams divided by 10 centimeters squared, we divide the values 5 and 10 and the units grams and centimeters squared to end up with 0.5 grams per centimeter squared. 5 pounds per cubic foot times 2 feet. We separate out the values and the units. 5 times 2 is 10, and we have the units. We have pounds per foot cubed, where we separate out the foot times foot times foot, and the foot in the numerator and one of the foot in the denominator will cancel, leaving us with pounds per foot squared as the units that are remained. Now, many units will use prefixes for powers of 10, such as kilo. You're familiar with kilometers. Well, here's a table of the more common prefixes that you'll encounter. You've probably heard of gigahertz and megahertz for 10 to the 6. 10 to the 3 is kilo, as in kilowatts or kilometers. 10 to the minus 2 is familiar for centi, as in centimeters. 10 to the minus 3 for milli, as in milliwatts or millimeters. 10 to the minus 6, as in micro, as in micrometers. 10 to the minus 9, as nano, or nanometers, that you'll encounter a lot as a photonic technician. Now, the units of measure must be included in all of your calculations in order to yield the correct units for your answers. So it is important that we continue to use all of the units. So let's look at a common physics formula, such as distance is equal to the velocity times the time, plus 1/2 the acceleration times the time squared. Here are the units of the metric system, for example. So for metric values, let's look at the units, how those units would work out. If we multiplied a speed in meters per second times a time in seconds, plus 1/2 times an acceleration in meters per second squared, times a second of time squared. You'll notice that the seconds here will cancel, leaving us with just meters. And here we have seconds squared divided by seconds squared will cancel, leaving us with just meters. So the distance results in meters, which is what we like to see, a distance in meters. What if the values of all of our speeds and acceleration and so on were an English system, as in miles per hour and miles per hour squared and hours? Well, we would hope then that the distance would result in a distance calculation of miles. The correct type of units are important: distance, speed, area, temperature, and so on, and you don't want to mix them up. And the correct scale of units are important too. Meters, feet, miles, and inches are all distance units, but we don't want to mix them in calculations, so we convert them. For example, if we are going to be adding distance of 1 foot plus 6 inches, we'll want to convert them in the same units of measurement. So we'll convert 1 feet to inches, which will be 12 inches, plus 6 inches equals 18 inches. You'd probably have done this anyways, but we wanted to be sure to do this in more complicated problems, and some conversions are not so easy, and for that we will need to use unit ratio. So let's learn about unit ratio and how that will help us not mix up the units and calculations. Unit ratios is really just a fraction that is formed by two equivalent quantities. For example, 100 centimeters is the same as 1 meter. So if we put 100 centimeters over 1 meter, it's really just equal to 1. Or 1 meter over 100 centimeters is also equal to 1. We can also have 1 foot over 12 inches, or 12 inches over 1 foot. Those are both equal to 1. Multiplying by 1 results in the same number, just changes some of the units around. So when we multiply by a unit ratio, such as 6 feet times multiplying by a unit ratio of 12 inches over 1 foot, we multiply the values. 6 times 12 over 1. And we separate the units, which would be feet times inches over feet. And you'll notice that the value 6 times 12 will be 72. And the feet will cancel in the units portion. And all we're left with is inches. So the result is 72 inches. So in general, we can convert a measurement. Say a measurement A in some given unit is a different desired unit to multiplying by a conveniently chosen unit ratio. Now, how do we choose that unit ratio? The numerator will be the desired unit we are trying to achieve, and the denominator will be the given unit that we started with. So we start with the number and unit before the conversion, multiply it by a unit ratio that we form, and the result will be the value and the desired units. So let's see how that works in an example. Suppose we have our distance of 10 miles and we want to find the same distance in feet. From the table, we find that 1 mile is equal to 5,280 feet. So we can form a unit ratio with that relationship. We can form a unit ratio of either 1 mile over 5,280 or 5,280 divided by 1 mile. Which one would be the right one to pick? Since our given unit is miles and desired unit is feet, then we'll use the second unit ratio because we want the desired unit to be the numerator. So remember that expression. The desired unit will be in the numerator. So the given unit is 10 miles and the desired unit is 5,280 feet divided by 1 mile. So here's our unit ratio, and then we have our values. We pull out our values out of our multiplication. 10 times 5,280 divided by 1. And then we pull out our units. Miles by feet divided by miles. And you'll notice that the miles will cancel, leaving us with just feet. And the resulting answer is 52,800 feet. Here is another example. Suppose we have a distance of 52,800 feet and we would like to find the same distance in inches. Well, this is just another application of a unit ratio. From the table of conversion factors, we can see that 1 foot equals 12 inches, and we can form one of two unit ratios. Either 1 foot over 12 inches or 12 inches over 1 foot. Which one should we pick? Well, our given unit is feet and our desired unit is inches, so we'll pick the second one, 12 inches in the numerator. Our given number is 52,800 feet. Our unit ratio is 12 inches over 1 foot. Our values, 52,800 times 12 over 1. Our units, feet times inches over feet, where our feets cancel, and our resulting value is 633,600 inches. So we have the distance of 52,800 feet is equivalent to 633,600 inches. Well, we can combine two conversions because all we are doing is multiplying factors. We can multiply two factors. So suppose we start with a given distance of 10 miles and we are asked to find the same distance in inches. So we are combining the previous two examples into one. From the table, we have our previous two relationships. The 1 mile is equal to 5,280 feet, and 1 foot is equal to 12 inches. So we can form two unit ratios now. We'll multiply by both unit ratios and we can cancel the given units, leaving the desired units. I expect that you can see the pattern that we're starting to develop here. We'll pick the unit ratios that will end up with canceling the units. Now, this one is a little more complicated, but you'll notice that we want the miles to cancel first of all. So we'll pick our unit ratio of 5,280 feet over 1 mile. Now, we have feet and we need to get to inches. So we'll now multiply 12 inches over 1 foot, and the feet will cancel. And so the result is that we'll have all of these values to multiply together. 10 times 5,280 times 12 divided by 1 times 1 and we'll have all of these units to multiply together, and most of them will cancel out except the one that we're left with, the desired unit. And the result will be the same that we had before, 633,600 inches. But you see how we did that in one big long calculation. So now I think we are ready to work on that opening scenario problem, where we had to deal with lots of different units together. Let's look at the equation again. We can substitute the given values and work with those units. So we substitute 33.3 grams per second for the delta M over delta T, the C value of 1 calorie per gram degree C, and a delta T of 17.7 degrees C. And we pull out all of our values, 33.3 times 1 times 17.7, and all of our units, and see how we cancel the units out. And you see what we are going to be left with. Calories per second, which is a heat flow rate, which agrees with what our formula should give us. And our result is 589.4 calories per second. So now let's look at some practice exercises that are in the back of this module. First thing we are asked to do is multiply and divide some quantities and obtain the correct number in units. So if we multiply 5 pounds times 10 feet, as we have seen in the text, we are going to multiply the values and the units separately. So multiply 5 times 10 and pounds times feet to end up with 50 pounds times feet, or more commonly shown in the physics books as foot-pounds. Second problem would be 100 newtons divided by 5 meters squared, which we could write as a fraction, 100 newtons divided by 5 meters squared. We will pull the values out, pull the units out, and evaluate the values and evaluate the units. There's the third example, 16 miles per hour times 0.5 hours. We will pull the values out, 16 times 0.5, pull the units out. In this case, the units, part of them will cancel, and the result will be 16 times 0.5 is 8, and the units remain are the miles. Here's another example, a little more complicated. 62.4 pounds per cubic foot times 10 feet. Again, we will have the values and the units out. We'll express the cubic feet as feet times feet times feet, so that one of the pairs of the feet will cancel, leaving us with just pounds divided by feet times feet, better known as pounds per foot squared. And the value will be 624 pounds per foot squared. Exercise 2 asks us to complete the table of factors, prefixes, and symbols for the measurement units. And you should be able to do this based on the table that is in the text. Now, exercise 3 asks you to change the power of 10 notation to a prefix that's applied to a unit. So if your result came out to be 5.6 times 10 to the third meters, what prefix would you put on that? Well, that would be the same as 5.6 kilometers or kilometers that we're used to saying. And the abbreviation for that would be km if you want to use the abbreviation. 6.8 times 10 to the 3 calories would also be 6.8 kilocalories. 10 times 10 to the minus 2 meters would be 10 centimeters, using that table that you just completed in the previous exercise. 5 times 10 to the minus 3 meters, what prefix would be appropriate for 10 to the minus 3? That would be millimeters. 3.14 times 10 to the minus 9 seconds, the prefix for 10 to the minus 9 would be nanoseconds. Table 3 then, we could use to replace the power of 10 multipliers with actual values, with prefixes. So if we had 10 to the negative 3 meters, we could use millimeters. 10 to the minus 3 grams would be milligrams. 10 to the minus 6 calories would be microcalories. 10 to the minus 2 meters would be centimeters. Exercise 5 asks you to rewrite 15,600 grams using power of 10 notations and kilograms. So we'd have to determine what multiplier could we pull out of the 15,600 to use a power of 10 notation, and you can see that you can divide 15,600 by 1,000, or 10 to the 3, which is the same as a kilo. So we'd end up with 10 to the 3 grams or kilograms for exercise 5. Exercise 6 is a good practice in verifying how the units work out in an equation, and this one asks us to do this in both English and SI units for the equation where the velocity is equal to the initial velocity plus the acceleration times time. A good physics equation that you may have encountered in one of your physics courses, where VF and VI are the final and initial speeds of feet per second or meters per second, and A is acceleration, feet per second squared or meters per second squared, and T is times in seconds. So in English, the way that that would work is you would substitute in those units for V, where feet per second, and acceleration is feet per second squared and times the seconds. And you can see as you expand out the seconds squared that one of those seconds will cancel out, and you'll end up with feet per second plus feet per second, which of course is a feet per second value. And you'll have a feet per second value on the left side of the formula and feet per second on the right side of the formula, which is a good result. In the metric system, very similar result. You'll have meters per second squared in seconds, and one of the seconds will cancel out, leaving us with meters per second plus meters per second on the right side, subsequent meters per second plus meters per second, and everything checks out very nicely, and the formula is consistent with the units of speed. Exercise 7 asks you to verify the units work out correctly for a little bit more complex equation where we have the electrical resistance is equal to the electrical resistivity in ohm centimeters times the wire length centimeters divided by the area in centimeters squared. And if you substitute in those units, you'll have centimeters canceling in the numerator and the denominators, and the result will be ohms equals ohms, which again, the units will be consistent in this equation. Exercise 8 asks you to convert 150 centimeters to millimeters. Now you'll note that 1 centimeter is equal to 10 millimeters, and so we'll use that as a unit ratio. So we'll multiply 150 centimeters times 10 millimeters over 1 centimeter, where the desired unit is millimeters up the top, right? So we'll group the values together and the units together, and the centimeters will cancel, leaving us with just millimeters, and the result is 1,500 millimeters. Exercise 9 asks you to convert 21 liters to gallons. Again, we'll form a unit ratio. Using 1 gallon is equal to 3.785 liters, and we'll have to multiply by unit ratio again. So we'll put the desired unit on top, and then that'll group us the values of 21 divided by 3.785, and the units will group together, so the liters will cancel, leaving us with just gallons. And those values will evaluate out to 5.5 gallons. Exercise 12 is a little bit more challenging. It asks you to convert 10.5 miles per hour to feet per second. This time we'll have to use 2 unit ratios to get there. We'll use the relationship of 1 mile is equal to 5,280 feet, and 1 hour is equal to 3,600 seconds. So we'll start with 10.5 miles per hour, and we want a result of feet per second. So we want to get feet in the numerator. So feet will be the desired unit, so we'll put that on top. and that way the miles will cancel. And we'll multiply by a second unit ratio of 1 hour over 3,600 seconds, so that seconds will end up in the denominator and the hours will cancel. You see how we're looking ahead? So we chose our unit ratio so that the units hours will cancel. Then we group all the values together, 10.5 times 5,280 divided by 3,600, and the result will be 15.4. And we group all of the units together, and sure enough, the miles will cancel and the hours will cancel, leaving us with feet per second in the result. And our resulting answer is 15.4 feet per second. Alright, well that concludes Module 2 for Mathematics for Photonics Education. I hope that this gives you some confidence to do the rest of these practice exercises and feel ready to move on to the next module in this course. Good luck!